Hello AP Physics students, this is Dr. Brinzi here, and this is lesson 9.1.1. We're starting off a brand new unit on heat and temperature, and I want to begin this unit by asking an essential question. What is temperature? Well, the objective of this lesson is that we're going to end up being able to describe the relationship between temperature and molecular kinetic energy in an ideal gas. Now, the reason I want to begin by asking the essential question, what is temperature, is because we kind of have this qualitative idea about what it is, but what is actually going on physically with temperature? We know that temperature has something to do with how hot or how cold something is. We have that intuitive sense about us. You can tell me a number for the temperature outside. We actually use these devices called thermometers to measure it, but what are we actually physically measuring? I mean, yeah, how hot or how cold something is, it's, but it kind of is nebulous. It's not well defined in terms of physics. So my mission today is to be able to give this a more physical definition. And the easiest way for me to do that is to consider how an ideal gas behaves inside of a box. So let's consider an ideal gas. Its collisions are elastic, which means we don't lose energy between collisions of molecules in an ideal gas. We have no attraction between the gas molecules in the wall or the gas molecules and other gas molecules. And they obey what's called the ideal gas law, which you may remember back from chemistry. I have given probably a different form than what you learned in chemistry. Maybe you learned PV equals N, and here you used a little n, and then there is an R, big R, and then capital T, which stands for temperature. I'm going to use this form of the ideal gas law because it's going to make a lot more sense for how I'm going to relate temperature with something going on in the physical world. Let's just remind ourselves of what these variables are in this ideal gas law. So we have pressure and volume, and then N, let me back up there. N is actually the number of molecules. Big N is the number of molecules inside this box of volume V. You're used to actually using the number of moles, but we're actually going to use the number of molecules. K is a constant, and that constant is called the Boltzmann constant, named after a physicist who did a lot of research with ideal gases. And then T, of course, is temperature. So how is an ideal gas going to help us connect temperature with something happening in the real world or the physical world? I want to start off by thinking about the pressure that is provided by the collisions of gas molecules with the walls of its container. So let's consider a small section of the container wall. So let's consider this our small section of wall, and this small section of wall is going to have an area A. And let's assume that gas molecules have the same speed in the x direction. And we're going to call that speed v sub x. What that allows us to, one of the things the other thing we're going to assume is that half of the molecules inside this volume are traveling toward the wall, and half of the molecules are going away from the wall. So that's the other assumption that we're going to make. And that's a pretty valid assumption, right? I mean, if you have gas molecules going in random directions, you could say that half are going toward the wall and half are going away. That seems like a reasonable assumption to make. So how many collisions are going to happen with this little section of wall in an infinitesimal time dt, a very small time? Well, here's our little area. Oops. Here's our area A. Okay. And there are the only molecules in the gas that could possibly collide with this wall are the gas molecules within a certain small cylinder. So I've drawn a small cylinder. And I'm going to argue to you that only molecules that are inside this small cylinder will actually hit the area A. Okay. Now, I have to actually tell you what the length of this cylinder will be. Well, if we are assuming that all of the gas molecules are traveling with a speed of Vx, then that amount, sorry, I had to actually pause the video there for a second. I was arguing here, what would the length of this cylinder be if I were to argue to you that only molecules that are inside this cylinder could possibly hit this wall in a time dt? Well, we know that all of these molecules, or we assumed all of these molecules, are traveling with a speed in the x direction given by Vx. If I were to multiply that times the time, dt, well, that would give me the total distance that a molecule could travel in time dt, and that would actually be the length of the cylinder here. So only molecules within this cylinder are going to have enough time within dt to actually be able to make it toward and hit the cylinder. Any molecules that are outside this cylinder are not going to possibly be able to hit this area A inside that time frame. So, what is the volume of the cylinder? The volume of the cylinder happens to be its area times its length. So, we could say, and I'm actually going to call this volume dV. So dV is equal to the cross-section area A times the length of the cylinder, which is going to be Vx dt. Inside this cylinder, there are the total number of molecules inside the box divided by V. That, in a sense, gives us a density of molecules. And then we have to multiply that density of molecules times the volume of this cylinder to get the number of molecules in the cylinder. So there are going to be N divided by V times dV molecules in this cylinder. And half of those molecules are going to collide with the wall. Remember, I said half because half of the molecules in this cylinder are traveling away from the wall, the other half are traveling toward the wall. And of course, it's only going to be the molecules that are traveling toward the wall that are actually going to collide with the wall. So the number of collisions that's going to happen on this area inside this little time frame dt is going to be 1/2 times N divided by V times dV. 1/2 of the total number of molecules. Well, that total number of I can replace dV, excuse me. I can replace dV. Ooh, something happened there. I can replace dV with this expression right here. And I'm going to get 1/2 N divided by V times A Vx dt. So that's the total number of collisions that's going to happen on this area inside an infinitesimal time dt. Well, now that I know the total number of collisions, I can actually calculate how much pressure the wall has to exert on the gas, because that, according to Newton's third law, that is the equal and opposite to the amount of force that the gas pushes on the wall. Well, how do I figure out how much pressure the wall must exert? Well, let's think about a collision of a gas molecule with this wall. It's going to come in with a momentum in the x direction, and that momentum is going to equal negative m times vx. I'm assuming that the negative direction in x is toward the left. Its momentum after the collision, now remember this collision is elastic, so it has to have the same speed going in as it does coming out. The reason behind that is because kinetic energy has to be conserved in an elastic collision. And if kinetic energy is conserved, and I am not moving this wall after the collision, it's going to stay in place, well, that means that this velocity after has to equal the velocity before. That is the only way that I can conserve both momentum and energy. Sorry, I had to pause there for a second. That's the only way that I can conserve both momentum and energy in this collision. So the change in momentum that this particle experiences before and after this collision is going to be 2 times mvx. Because I take this minus that, and if I take minus this, that's like adding mvx, so I have 2 mvx. So the total change in momentum is 2 mvx. Now, according to the momentum impulse theorem, which we learned way back in unit number 4, we know that the impulse is equal to the change in momentum. And if you remember, what is impulse? Impulse is a force applied over time. So the amount of force times dt is going to equal 2 times m times vx. That means that I could write down the force that each molecule exerts on the wall, and that would also mean the amount of force that the wall exerts on each molecule, and that is going to be equal to 2 mvx divided by dt. That is the force from one collision. Now the force from all the collisions that take place in dt, so I'd have to take the force, this force from one collision, times the number of collisions that took place. So the total amount of force that the wall exerts on the gas in dt is given by this equation. Okay, this is the amount of force in one collision. This is the total number of collisions that I came up with on the last slide. So if I multiply those two together and I do some simplifying here, the 2 and the 1/2 will multiply out. There is a dt that divides out, and I end up with m times n times a divided by v times vx squared. So if I have the amount of force that the wall has to exert on the gas, then I also have the amount of, I could calculate the amount of pressure just by taking force divided by area, and that is going to be give me m times n divided by v times vx squared. Now let's go ahead and plug this pressure into the ideal gas law. So we have, so let's go ahead and plug this into the ideal gas law. So here's our ideal gas law, P times V equals NKT. And then I just am going to replace P with what we just came up with on our last slide here. We're going to multiply that times V, and we're going to set that equal to NKT. And let's do a little simplifying over here. Oops. Ooh, I went a little too far there. Didn't give you the result here. Well, it turns out when you simplify, It looks like a v divides out, and then there's an n on both sides of the equation. So it turns out that m times vx squared equals k times t. Well, maybe you recognize this expression, m times vx squared. Maybe you would recognize it more if we put a 1/2 in front of it. But I've only given you the collisions that happen in one dimension. We have a three-dimensional box here. Now, everything that I've given to you so far really doesn't depend on whether I call this the x direction, the y direction, or the z direction. So, each of the three directions, each of the three dimensions, will have an equation that is similar to what I just wrote. So I'll have an mvx squared equals k times t, I'll have an mvy squared equals k times t, and I'll have an mv squared equals kt. Well, in reality, the velocity of a particle is going to have an x component, a y component, and a z component, just like this vector has an x component, a y component, and a z component. The question is, can I somehow use this information to tie that in with the speed of this particle? Well, in order to do that, I am going to use a little bit of trigonometry here. So in order to get to the point 2, 3, 5 in three-dimensional space, I have to go a distance 2 in x. So we'll call this the x component of our velocity vector. I would have to go a distance of 3 in y, so let's call that the y component of my velocity vector. And then my z component, which goes all the way up here. Well, actually it doesn't go up there. Now this is kind of look a little funny, but because I'm trying to project 2 dimensions, or 3 dimensions onto 2, this is going to look a little odd, but if I were to extend a line from this point all the way over to the z-axis, I would actually end up at the number 5 right there. So let's consider that the z component. Well, this velocity vector has a magnitude of v, which I'm going to call the speed of the gas particle. We can use some trigonometry. This is a right-hand triangle, and this is probably a right-hand triangle you're familiar with dealing with. And we can actually calculate the length of this line from here over to here by using the Pythagorean theorem. And we're going to end up with a value of the square root of vx squared plus vy squared. And then I end up having another right triangle that actually goes up in the z direction. So 1, 2, and then this would be the hypotenuse of the triangle. So if I wanted to calculate what v is, I would take this squared plus this squared. So by the Pythagorean theorem, this squared is equal to this squared plus this squared, and this is actually vz, so that would just be vz squared. Well, let's square the square root, and we end up with this result. V squared equals vx squared plus vy squared plus vz squared. So this actually is the Pythagorean theorem in 3 dimensions. Well, what that means is if I were to add up all 3 of these things, mvx squared plus mvy squared plus mvz squared, what would I get? Well, I would get 3 times kt, right? Because each of those is equal to k times t. I can do a little bit of factoring out. I can factor out the common factor. So I have m times vx squared plus vy squared plus vz squared equals 3kt. And by the 3-dimensional Pythagorean theorem, I know what this equals. That is going to simply equal v squared. So I have mv squared equals 3kt. Now, if I were to take 1/2 of this, I would have the kinetic energy of my gas molecule. So the kinetic energy of the gas molecule is equal to 3/2 kT. That's a really important result. But I'm not quite finished yet, because you might object. And you might say, hey, Dr. Brinzy, you assume that all molecules in the gas have the same speed. Is that really true? And you would be right in saying that. And I would have to say no. But it is helpful. And let me show you why. Now, to give you a more tangible example, let's talk about LeBron James. And LeBron James, over 4 games, let's say scores 32, 34, 38, and 40 points. And over that 4-game span, he scores a total of 144 points. His average over that 4-game span is 36 points per game. Now, if I were to take each of those game scores and replace it with his average, so let's cross that out and replace it with 36, cross that out, replace it with 36, cross that out, replace it with 36, cross that out, replace it with 36, I would still end up with the same total number of points over that 4-game span, wouldn't I? Absolutely, I would end up with 144 points. So, how would I apply this law of averages to a gas molecule? Well, gas molecules have different kinetic energies, Ke1, Ke2, Ke3, Ke4, and let's just pretend for now that there are only 4 gas molecules inside our box. We know there are way more than that, but I think you would get the picture after this. We'd add up all those kinetic energies, and we would get a total kinetic energy for the gas. Now, I could replace each of those with the average kinetic energy for each gas molecule, and I would still come up with the same total kinetic energy in the gas, right? Well, that's like saying that we are assuming that each of these molecules has the same speed. So in a sense, we can assume that molecules in the gas have the same speed as long as we're talking about the average speed. So how does this change the result that I just told you? And what is the big point of all this? I just spent a long time telling you that the temperature can be thought of as a measure of average kinetic energy of molecules in an ideal gas. I just proved to you that the average kinetic energy of a molecule in the ideal gas is equal to 3/2 times this constant K times the temperature of the gas. So temperature can be thought of as a measurement of average kinetic energy of molecules. That's a pretty huge result. And that's the physical connection now that we actually need. Until now, we were just thinking about temperature as how hot or how cold something is. But now we have a physical tie-in with the kinetic energy of molecules in a gas. Actually, average kinetic energy. Now, one thing that we often talk about when we talk about ideal gases is what is called root mean square speed. And here's why we are so interested in root mean square speed in an ideal gas. The average kinetic energy is equal to 1/2 times m times the average value of v squared. It's this thing that is equal to 3/2 kT. The average kinetic energy comes from the average of the speed squared, not the square of the average speed. Okay, there is a big difference. This right here is the average of v squared, where I take v1 squared plus v2 squared plus v3 squared dot dot dot, and I divide all that by the number of molecules I have in the gas. That's not equal to, I know that this kind of turned out crazy here, that's not equal to taking the average velocity of each molecule, dividing that by n, and then squaring that value. These two things are not equal. And it's not this one that we're interested in, it's actually this one we are interested in. Now, taking the square root of this value is like taking the root of the average, and that is what we call root mean square. We are taking the root of the mean of the square value. The root of the mean of the square. So VRMS is that common speed that all the gas molecules have if we're assuming that all of them have a kinetic energy equal to average kinetic energy. So that's why we're so interested in talking about root mean square speed of a gas and not in about the average speed of the gas. Okay, that's all I have for this lesson, and I hope that was informative. I hope it was educational. I know that it's a completely new topic, but we're going to have an opportunity to work more with it in class, and I look forward to seeing you then. Bye.